I'll be doing I'll be doing some angle chasing geo. This is going to be basically problems which only use angle chasing. And yeah, feel free to interrupt at any point if you have any questions. Just ask. Totally fine. So great. I assume everybody knows what an angle is. Great. So basically, that's mostly like the prerequisite. I'll paste a problem. So is the problem visible?
Yeah.
Great, great. So try the problem for some time, and if you have any ideas, just speak. Like even though you think it's like not useful or anything, just speak. Because of course, I don't expect you to solve the problem in 5 minutes. It's great if you can, but just keep on saying ideas. Also, instead of using chat or like the reaction, it would be better if you can unmute because it's kind of hard to check. But then yes. So I'll start with the diagram. Also, I'm sorry for the diagram going bad. It's hard to draw that. So ABC is an acute angle triangle. M is the midpoint of minor R. A circle omega touches. Oops. It's kind of hard to draw. Uh, yeah. Assume this is a circle. Circle omega touches AB and AC at points P and Q. We want to show the
Touches here
length.
means it's tangent.
Yeah. Touches means it's tangent. So the circle omega, I'll just write it here. Omega is tangent to AB at P and to AC at Q. So omega is tangent to both of the sides AB and AC at P and Q. And we want to show that the length of BP plus the length of segment CQ is equal to the length of segment PQ. This is V bound. So if at any point you have any ideas, feel free to speak.
We can, I guess, make a point R on PQ such that PR is equals to PB, and then
Okay,
try to show that QRC is equals to QCR.
that is a great idea. That is a wonderful idea. So the aim is to we find a point R on PQ such that BP is equal to PR. Now if BP is PR, now we want that QR is QC. If we can show this, then notice the length of PQ. Okay, I'll just scroll up so the diagram is visible as well. So the length of PQ is actually equal to the length of PR plus RQ. And if we know PR is equal to BP, so if we can show that QR is also equal to QC, we would be done, right? So if we can just show this, our life would be done. Is this fine for everyone? Is there any questions at any point? Just feel free to unmute and ask. I'd assume there are no questions. So this idea of finding a point R such that two lengths are equal and showing the third length is equal is very useful. And the reason I basically wanted to do this problem is just was this idea.
Also, we can show that angle APQ is equals to angle AQP by equating both the angles to PMQ.
That is perfectly correct as well. So I'll move slightly here. I'll go down. So there's a fact for people who, if you don't know this fact, it's another very useful fact. So if you have a circle and a line tangent to it, it's tangent at point, say A. And if you have point B and C here and D here, then we have that angle BAD is equal to angle BCA. This is a very useful fact. Keep this fact in mind. And for the proof of this, I'll just take it as an exercise. Try proving this. But yeah, keep this in mind. So what someone said is they wanted to use this fact on APQ. So if you look at this, we have a line tangent to our circle omega. This line is tangent to circle omega. And P and Q are points like this. M is point here. Using our lemma, we get angle APQ is equal to angle PMQ. And the same thing we can do for Q. Because the line AC is also tangent to the circle. So we get angle AQP is equal to angle QMP. Right? And just because these two people are equal, so these two guys are equal as well. So this
So
means that
now if we just equate the angles, we need to prove that PBR is equals to QCR.
1 second. We want to show PBR is equal to I'll just write it. What do you want to show? Angle PBR
is equals to angle QCR.
Okay. Can you explain this how?
So we get that APR is equals to twice of angle PBR.
Angle
And so is
APR is equal to twice of angle. I'll just write this explanation for everyone. This is equal to angle PBR plus angle PRB by exterior angle. And we know PR is PP, so this is twice of angle PBR.
and we also know that APR is equals to angle AQR.
Yep, which is
So
equal
we
to
need
angle
to
AQR.
equate it.
Correct,
And AQR, we need to prove that AQR is equals to twice of angle QCR.
correct. We want this because ACR is equal to, by again exterior angle, we have, I'll just slightly zoom out so that the diagram is visible as well. Angle QRC plus angle QCR. And we want to show QR is equal to QC, remember. So if we can show this guy, we would be done. So if we can show this equality, we are done as well. We have something in chat.
We did
Join.
not need to use that tangent sequence theorem.
Yes, we did
Because the
not need to use
arithmetic.
that. You're correct. The chat message I just read, that is correct. That tangents from A to a circle have equal length. Someone also mentioned that AM is actually the perpendicular bisector of PQ. Can you prove it? Whoever just said that. Like, how did you get this? M is the midpoint of arc BC, not BC. Like on the circumcircle, a point on the minor arc says that MB is equal to MC. Fine.
We can just say that because AM passes through the incenter, so and P and Q, AP equals AQ. So the point on the incenter is the angle bisector of PAQ. So that is also the midpoint. And the
That is correct. That is correct as well. So what you want to say is that the line AM is the angle bisector of angle BAC. And in an isosceles triangle, the angle bisector is the perpendicular bisector. Right? So I'll just state this fact, another super useful fact. If we have a circle, triangle, ABC, a midpoint of arc, point M, such that MB is equal to MC, we have that this angle is equal to this angle as well. This is also very useful. This is as a quite easy proof. Let's call this angle X. By MB equal to MC, both of these are angle in X. And now look at the angle inscribed by segment MB. This is X because of this angle BCM, but this is also angle BAM. So this must be X. Now we look at the angle inscribed by MC. MBC is MS. And that useful fact, some people seem to know. If you don't know, no problem. Keep this in mind. So again, I'll just repeat the proof. We got AM is the angle bisector of angle BAC and hence the angle bisector of angle PAQ as well. And AP is equal to AQ and angle bisector, we have these two angles are equal. This means it's actually the perpendicular bisector. Great. Just copy this diagram so that you can move it down and it doesn't get crowded. You get bigger. Great. So we got some information that M also lies in the perpendicular bisector of PQ, which means the less segments MP and MQ are equal. This also means that these angles are equal. Can we say something about more then? Like something with respect to these angles?
So angle PQM will be equal to angle BPM.
Angle, I'll change color because I think red is not so visible. Angle PQM is equal to angle BPM. Perfectly correct. Which means we found another angle which is red.
And similarly, angle MQC equals angle MPQ.
Perfect. Perfectly correct. We have more angles. Great. What we wanted, remember, we know BP is equal to PR. We want QR is equal to QC. Or we can also say this is an angle condition. Angle PBR equal to angle QC. Oops. Yep.
Or we could also say that PM is the perpendicular bisector of BR.
Correct. That is a great thing. Again, notice PBR is an isosceles triangle. PBR is isosceles. Because we have PP is equal to BR. Sorry, PP is equal to PR. And PM is now the angle bisector. The red angles are equal. Angle bisector is also perpendicular bisector. So MP is perpendicular bisector of PR.
So it suffices to say we name the intersection of MQ and RC as K.
Okay. If we call this point K,
Then and the other corresponding point L, then if we prove MKRL is cyclic, we're done.
And
perfectly
we
correct. Yeah, go ahead. Someone was saying something?
No, I assumed something wrong.
No problem, no problem.
Actually, I thought that QRC plus PRB is equals to 2x, so that is 180 minus 2x, and we also know that PMQ is 2x.
No problem, no problem. It's okay, we have a lot of ideas.
We could also show that LK is parallel to BC. So RLK is equals to RBC.
I'm sorry, what? I'm sorry, I couldn't follow that. Could you repeat?
LK must be parallel to BC. We need to prove that maybe.
Yeah, we want this because L is midpoint of PR and we want K to be point of us. Isn't there a spiral similarity? Okay, don't go to spiral similarity. But I get what you're trying to say. Think of something easy. Think of something we have. We got MP as the perpendicular bisector. Let us use that mode. We have MB is equal to MR, right? We have MB is equal to MR.
Oh
What do we
yeah.
want?
So we want MR is equals to MC.
We want MR equal to MC. But MB and MC are equal. So we are done.
We are done. Okay.
Yeah. Great. Does everyone follow the proof?
Yes.
Perfect. So the main idea of this problem was to, first of all, finding this point R. This is a super useful idea of like breaking, if you have something like a length is equal to sum of two lengths, we can find the point R so that you have equal lengths now. And now angles can do great help. That's what we did. We found the point R, we chased a lot of angles, and life just started to make sense and stuff worked out. So, is there any questions about this problem you can ask? If there's no questions, we'll move on to another problem. Is there any questions to anyone? You can just please ask. I'd assume there are no questions, and we should go with another problem. So we have ABCD is a quadrilateral, pretty specific quadrilateral. With AB equal to BC equal to CD. P and Q are points inside ABCD, such that AP is equal to BP. It's also equal to CQ and also equal to DQ. Now we draw parallel from P to AC and parallel from Q to AD. Okay, I'll actually draw these lines in a different color. These are not collinear. These are parallel. At a point T, we want PT to be equal to TC. So this is parallel to this. This is parallel to this. I'll actually draw BT and TC in another color so that it's visible that the lines are not the same. Like blue line and red line are not the same. Neither is a white line same as blue line. So try it for some time. And if you have any ideas, just speak. Congruent triangles. Which triangles are congruent? Is you mean okay. APB is congruent to CQD. That is perfectly correct. Angle between lines PT and QT is equal to angle between A. Yep, that is perfectly correct as well. So angle PTQ is equal to the angle between lines AC and BD. Perfectly correct because parallel lines make same angles. So you have parallel line, every angle is basically the same. So it's kind of like a one trick problem, I'd say. It's just that it's kind of like a leap of faith that you have to make. After that, it's much easier. Currently, we have no information about T. And there are so many equal lengths. If you have so many equal lengths, you probably expect a lot more lengths to be equal. Maybe choose a point X such that BT, choose a point X and CD. Wait, maybe choose a point X and CD such that BT is equal to TX. Is that what you mean? Like you want to choose a point X somewhere here such that BT is equal to TX, and you want to show that X is C. Wait, 1 second. You want to choose a point X and AD such that TX is equal to TP is equal to TC. Okay.
Should this point necessarily exist?
Yeah, that's another question. This point might not exist as well. Because, look, if you draw the circle centered at T passing through B and C, basically have some circle like this. There would be like some condition, some quadrilateral where this never intersects the line AD. So the point X might not even exist at times. But anyways, what did you wanted to do with X? If that's a great idea, we can probably find some way to finish in a different way. Ah, I see. No problem.
Do we claim PT equals QT and then prove that PQ is parallel to BC? So T will lie on the perpendicular bisector of both of them.
Wait, slow down. What did you say? BT equal to?
PT.
Oh, we want PT equal to QT.
And PQ parallel to BC.
PQ parallel to BC. If we can get both of the things, then yes, I agree we would be done. What would both of these things to be done? Let's look at the second condition. Is PQ always parallel to BC?
Yeah, it isn't. We can vary how we want to.
That is the sad part. But yes, that is a great idea of like making conjectures. Try to make conjectures which make the problem slightly more handleable. That is a perfectly nice idea. Sure, all of us make wrong conjectures. And like proving your conjecture is wrong is also a good thing. Try to make a conjecture. What would T satisfy more, which makes the problem a lot more tractable? Because right now we have no idea how to even think about T.
Can we construct T so that BT is equal to PA?
Indeed. That is the key idea. So just because the diagram has so many equal lengths, you'd expect a lot more lengths to be actually equal. So another conjecture that we had is BT equal to AP. If this is true, assume this is true, what happens then? Notice BT,
BPT is isosceles triangle.
Yeah, PPT is an isosceles triangle. BAC is also an isosceles triangle. We have BAC is an isosceles triangle like this. We have PPT is another isosceles triangle like this. Does this mean PT is parallel to AC?
Wait, can you repeat?
We have BAC is an isosceles triangle with BA equal to BC. BPT is another isosceles triangle with BP equal to PT. Does this mean PT is parallel to AC?
No.
Are you sure?
Oh yeah, PT is, wait, PT is already parallel to AC, no?
Haha, I'm
Okay.
just saying in a different
Okay,
way. Like,
yeah,
forget
yeah.
about the problem. There's a different kind of an idea.
But this is not necessary until and unless the angles are also equal. Like ABP is equals to CBT.
Yes, that is correct. So we need these angles to be equal. Right? Now let's go back to our problem. If we had BP is equal to BT, if we had that, then we get this isosceles triangle is parallel. So we must have that both of these angles are equal, right?
Yeah.
Are these two angles equal? Right now, assume that the problem is true. Assume that BT is equal to BP is equal to AP, all of those lengths are equal, and PT is parallel. First, assume the problem is true, then we'll try to extract information
Yeah,
what we use.
Congruent angles.
Precisely. So, okay, I'll just repeat what we're trying to do. We hope that BT is equal to AP because there are so many equal lengths. Now we are trying to show that is this even possible? Like, let's just check our conjecture. So in this case, we will just assume everything. We'll assume that BT is equal to AP. We'll assume PT is parallel, we'll assume TQ is parallel. Then we get some more information or like some way to prove it. And then we retrace the proof back so that we don't need one condition. Does that make sense of what I'm trying to say? In some sense, a much easier way to say it is like, say you want to prove 3-point circle linear. Or like say 3 lines are concurrent. I assume that both of these 3 lines are concurrent. I assume that all 3 lines are concurrent. Then I find some property more, which doesn't use the concurrency of this line. Then I prove this property, and that implies the concurrency. Does that intuition make sense of what we are trying to do?
Yeah, got it.
This is what we'll do here.
Oh, wow.
Someone have any questions?
No, that was mistake.
Oh, no problem.
So if we somehow equate the angles, then maybe then we will able to say that the triangles are congruent, and so BT will be equal to TC by both the congruent triangles of the sides.
Precisely. That is perfectly correct. First of all, does everyone follow the equal angle and congruence condition, right? Like in a triangle, in an isosceles triangle, we have BAC is isosceles triangle, BPT is another isosceles triangle, and we want PT parallel to AC. In that case, we want these two angles to be equal. For both of these angles to be equal, let's go back in our problem. We wanted both of these angles to be equal. And these angles are equal because AB is BC, and the triangle ABP would turn out to be congruent. We don't know this yet. We're assuming BT is AP. Then we would be done, right? So what someone said is that if we...
in the congruency, BCT.
Oh, sorry. Yeah, I messed up the order. Let's try this red, BCT. Great. So if we can force those angles to be equal, if we force these angles to be equal somehow, we would get the parallel, correct?
Yeah.
So if I define the point S such that I'll label the point, so this is A, B, C. If I define a point S such that SB is equal to SC is equal to BT is equal to AP. We know AB is equal to BC. So we get the congruence that we wanted. ABP is congruent to BCS. We get both of these angles are equal. We know this is an isosceles triangle. So this implies PS is parallel to AC. Correct?
Yeah.
Now we can do the same here. We had a point Q, we had D, CQ is QD, and CQ was also equal to BP as well. So again, we have the congruence. This is also congruent to CDQ. And this again implies SQ is also parallel to PD. Right?
Intersection of two parallels, maybe two lines. There's only always one point. So S
So
is
always
equal.
one point. So S must be T. And we wanted to show that BT is TC. We literally constructed S so that BS is S. Right? Does everyone follow the proof?
Yes.
So the main part of this proof was the leap of faith that we made. That just because so many lengths were equal and to handle some condition on T, would that more things be equal? Like a big leap of faith that we made, and then the problem made a lot more doable. Like sometimes this is like very useful. Like sometimes a lot of conditions are true, and then you want that something more should be true. Like you hope something more should be true, and the problem becomes a lot more tractable.
I think the use of the isosceles triangles was also very important, like how it gave parallel lines and how the angles should be.
Yep. That is also very true. At the equal lengths and the concurrencies everywhere, that was pretty useful as well. So does everyone follow the proof? I hope everyone does. If there are any questions, feel free to ask. I assume there are no questions. Let's go with another problem. Again, try it for some time. If any ideas, feel free to say. I shall draw the diagram.
Sorry, can I just ask something?
Yeah, sure. No, go ahead.
In the previous problem, how do we guarantee the existence of such an S?
Oh, sure. So first of all, okay, I'll say this in a different. I'll just go there. If we want an existence for point S, such that SV is equal to SC is equal to some fixed length, correct?
Yeah.
So all we need is to make an angle, fixed angle here. And if we can make this angle, we can get S. Correct? And that's
I see.
exactly what we need. Or a different way to state this, if we know the existence of a point P, we can just reflect P about the angle perpendicular bisector of AC. Because that's what we proved by the congruence. If S exists, it must be that. And if we can find S from like PS parallel to AC, then S must satisfy the property. So S must exist. Right?
Yes, okay.
Great. Is there any questions for anyone else as well? Feel free to ask. Okay, sorry. Okay, I assume there are no questions, and let's move to another problem. So ABC is a triangle. Point D and D are on segments AB and AC. So that AD is equal to AE. The perpendicular bisectors of BD and CE intersect minor arcs, maybe at points F, point G. Then show that the lines DE and FG are either parallel or the same. Basically parallel, like same as just special case. We want to show the lines are parallel. Well, actually, oops. So, they actually look parallel. Okay. Try the problem for some time. Feel free to say any idea that you have. And yeah. I'm sorry,
So-
what do you mean with AB equal to AC? Like the chat message. Are you talking about the special case when AB is equal to AC? Yes, the problem is true like always, whenever you have an acute link.
So if we look at the idea from the previous problem, it's almost the same. So we have to prove angle, since we have to prove FG is parallel to DE, it's equivalent to proving AF equals AG.
AF equal to AG. Wait. How is this like implied?
Actually, just a second.
I guess it should be the intersection of FG on AB and AC. That must be equal.
Yes.
Like I have an idea.
Yeah, go
Uh,
ahead.
If we extend FD and let it intersect at a point X on the circumcircle, and then
Stop. Okay, now that is the key idea. So, okay, we have FB is equal to FD. We have GC is equal to GE. That's basically the perpendicular bisector condition. These two lines are irrelevant. Like the perpendicular bisectors are itself irrelevant. The only thing that's relevant is that FD is equal to FB and GE is equal to GC. Now, the key idea is that whenever you have one segment, you have a circle, one point, and a segment which is like this, always extend it to meet the circumcircle. Just always do it. Like if you have anything of this sort, a segment with one point of the circumcircle, or a nice circle, a nice point which you want to care about, want more information about, extend it. It's super helpful. You find a bunch of angles. For example, in this problem, it's pretty hard to actually get started or do anything. But as soon as you draw these intersections, life becomes a lot more smoother. What do we call them? Let's call them X and Y. Now, we have some great angle conditions going on. Can you find them? Try finding like the angle condition. Like some more properties about this one. But oops.
So I guess it's same like proving f dash g is no.
Indeed. I'll let everyone try this for some time. I'll zip link the message in chat.
We can say that GD sorry YDEX are cyclic.
I was unmuted. I was on mute, sorry. Okay, so you said YDEX cyclic. Do you want to show that or did you prove that?
I proved that like we
Okay.
know that XFG is equals to XYD.
XFG is equal to angle XYD, correct?
XYE.
XFG, XYE, yeah. Yep.
And so also we know that okay, we need to show that. My bad. We need to
Yeah,
show that.
we want XFG to be equal to angle XDE. So we want to show down want angle XYE is equal to angle XDE. This is equivalent to showing XYDE is cyclic. Oops. Hmm.
Since
Okay.
AY equals AD equals AE equals AX, they are cyclic.
Yep. Okay, so let's find that angle condition now. We know angle FBD is equal to angle F. Oh God, I cannot write it. FDB. Now angle FBD is equal to angle FBA, which is also equal to angle FXA. Great. Because we want everything in X and Y. And let's now see where does angle FDB go. This is equal to angle XDA. So we get angle FXA is equal to angle XDA. Let's go up. Let me mark these angles. Angle FXA is this angle. Angle XDA is this angle. Wow. So that means AD is equal to AX. Similarly, we can prove AY is equal to AE, but AD was A. So all of them are equal. So we get this length is this length is this length is this length. This means circle centered at A with radius, whatever this thing is, passes through all these points. Hence, they're cyclic. Great. Does everyone follow the proof?
Yeah.
So the key idea was actually making FD let it intersect at X, taking G and letting it intersect at Y. This is like super useful. If you have a segment or the nice circle, 1 point on it, just extend it. This problem is not that easy, or like I do not know any solution. Instead of like bashing or something which does not introduce points X and Y. So if you don't introduce 0.6 and y, it can be like seriously hard. But if we do it, it become a lot easier. So just keep this in mind. Super easy.
Do you remember the source?
The source is IMO 2018 Lima. Okay, great. Now let's find another problem. We do a slightly harder problem. Let's try. Let's try this problem for some time. Draw diagram. Okay, actually, I would not draw diagram. Are you sure that is true?
In lines BC means through line BC.
Okay. I think. Okay, fine. That is true. That is correct. Okay. So if someone has said that, I will draw the diagram. The reason I wasn't drawing the diagram is because I actually wanted to emphasize if you have a quadrilateral geo with a lot of restrictions, these are not big restrictions, but this is a big restriction. It's secretly, like generally, there's secretly a triangle geo, just stated in a different way. So like first I'll draw a rough diagram. Like we have ABCD something like this. And we have this angle is equal to this angle. So someone said, like the circumcircle of ABD, when I reflect this about BD, I get this. So looking at one particular triangle, either ABD or CBD, makes more sense. As in, like, it's not a quadrilateral anymore, it's basically a triangle. So if we let's wait for circumcircle. If we start with ABD, and if we take the circumcircle, should run circumcircle. Reflect it about BD, take any point C on it, such that the obtuse angle conditions work out, we get a desired C. That's exactly what we want. The triangle wasn't really so the angle condition wasn't really big of an issue. Like basically the quadrilateral geo became a triangle geo. No? Just better. I'll erase the circles. Diagram doesn't get complicated. And now we want the reflections of A in lines BC and BD. There's E, this is 90. There's F, this is 90 as well. And these lines intersect K, N. Now we want to show these are actually tangent. It's a bad circle, but just believe it. It's hard to draw. Just believe both of these are circles. Correct. Smart way down very.
Can you show the problem?
Sure. Here's the problem. I'll delete this guy. It's 90. Everything is visible, hopefully. I'll try the problem for some time. That is a great idea. Just because we knew the circumcircles of ABD and BCD are reflections, let's start by reflecting A over BD. Some point right here. Let's call it A prime. So one thing we know is that so circle and a line. And just because we already have a lot of reflections of A, we should start. Let's try reflecting A over BD. So one thing we know is that B A prime CD is cyclic. Can we get some more information?
can you please re-explain how you introduce point A dash?
Oh, A dash is just a reflection of A about BD. All right, okay. A dash is reflection of A about BD. So just because it's reflection and like we get these angles are equal, hence we get the cycling. Right? Any questions? Is this fine?
Yeah.
Great, great. So can we find some more properties about A prime? Like what even are the circles PEK?
About A dash.
Yeah, about A dash, which somehow hopefully is related to PEK or DFI.
Would A dash be the point of tangency?
Okay. Who knows? It's a great conjecture. Is A dash point of tangents? If it were the point of tangency, let's assume what we did. Let's assume it. What are the conditions that it must have? First of all, it must even lie on the circles, right? Like A dash must lie on BEK, A dash must lie on its FDL. Is any of that true? Can we say prove? So, for this to be true, first sub condition is like is EKB A prime cyclic. Diagram might be false. Don't go with the diagram. It doesn't look on the circle. The diagram is horrible anyways, but like
Yeah, EKB A dash R cyclic.
indeed, how do you prove it?
So angle KEB will be equal to
KEB.
angle BAK,
Yep,
and that's going to be equal to angle BA dash K because A dash is a reflection of A.
correct,
Would be
correct. And that implies cyclicity. I'll explain this again. It's just reflections. We have this guy is equal to this guy because E was reflection of A about BC. And now we reflect A about BD, K lies on BD. So again, this. So indeed, the diagram is pretty bad, but this is true. So must be either be true by symmetry. So DFL, that's not an egg. L A prime is also cyclic. Great. Yeah, I'll. So our conjecture that the point of tangency A prime hasn't been proven false. It might be true. Might be true.
Because the circles could intersect at a second point, which we
Yeah.
that
Yeah. Yeah. Great. Okay. So if we want it to be true, and generally, if you have such a nice point lies on two circles that you want to prove is tangent. Like basically we prove that A prime must be the point of tangency, right? If it is the point of tangency, it must be like, okay, we proved A prime lies on both circles. We want to show the circles are tangent, which means A prime must be the point of tangency, right? So our conjecture must be true. Great. So how do we prove two circles are tangent? With angles, of course. So I'll
Maybe
just-
the centers are collinear and A lies on the centers.
that is one way, that is a great way. But if you just want to consider pure angles, is actually a nice thing which we can prove. So if this is a different diagram, consider this like a different thing. Yeah, what someone said in the chat. That is basically what we try to do. So say this is point A. This is a different problem for, don't confuse it with the previous thing. We have two circles intersect at C. We want to show the tangent at C. So if we can show that angle ACB is equal to angle ADC plus angle BEC, this is sufficient. This is sufficient for two circles to be tangent. Why is this true? As someone said in chat, if we draw the tangent through C to say this circle, then we get this angle is equal to this angle. Now, if we prove this, that would imply this other guy is also equal to other guy, similar to what we did in the first problem. And that would mean that this line is also tangent to the other circle. So this is a pure angle condition which actually is sufficient for to prove two circles are tangent. Is this fine with everyone?
Yeah.
Great. So going back to our problem, we need to somehow relate that fact and prove it here. What angle should we consider?
BAD is equals to
Yeah, the best angle is literally BAD. BAD is equal to
A plus DFA.
BA prime DL. Let's go with
prime.
BA prime E plus angle. No, wait, I messed up.
A prime.
Yeah. DEA prime plus angle DFA prime. Okay, we want this, right? Also, I'll take this diagram down. Wow. OneNote is smart. Which is Control C. Control C. Great. Okay, I'll rewrite what we wanted. Angle BA prime D is equal to angle BEA prime plus angle D. Can I find? Yeah, this is what we wanted. If we can show this, we would be done. So our entire life now is remaining to prove this. How do we prove this?
Maybe we could first no, that is
Now notice that this has removed K and L from the problem. Right? So we don't need KL and L anymore. So if we draw a new diagram, we have ABD. Reflection of A. Okay, I don't see this. This is the reflection of A about BD. Some point C is that the angle are equal. It's equal to this guy. So not we can reflect this right here. I mean, this is getting complicated. Let's just go back to the result. Whatever. Let's try to prove this.
Okay, so A prime, E is all three of them lie on a circle with center B.
Indeed. Yes. Go ahead.
Just so then
Yeah,
we
take
could
it.
okay, yeah.
That is a great idea. Perfect. So if we just look at this sub picture, right? We are looking at this angle, right?
Yeah, we could look at BA dash.
We can look at this angle as well.
But aren't we done like we know that BEA dash is equals to BAA dash, and we also know that BA is equals to BAA dash, BA dash.
Wait. Slow down. What were you saying?
BEA dash is equals to BAA dash.
BEA dash. This is equal to BAA dash. This is not true. BEA dash is equal to angle BA dash E.
Okay, yeah, I saw it through a different.
I think
Okay.
I've got um, B E A dash equals to B K A dash equals to B K A.
Indeed, correct. BEA dash is equal to angle BKA dash. Again, now let's reflect everything back over BD. This is equal to angle BAK. No, sorry, BKA. I mess up this. Correct.
You said we just get rid of the K and L points.
I had a different idea in mind. This also works. I had the circumcenter idea in mind. Like from this angle, you can relate it to this angle. Like this is equal to 90 minus theta. If this is theta. That was my idea. But sure, this works as well. Okay, so now in this case, like you can always say this, you either eliminated K and L or you eliminated E and L. Same thing. But now this actually eliminates A prime and not C, A prime at least. But so we have ABC, sorry, ABD, C is somewhere here. Oops. KL. We want to show the sum of this angle. White plus blue is equal to red. That's what we want, right?
Yeah.
How do we get that?
BCD is also red.
Yep, BCD is also red indeed.
then we get the cyclic quadrilateral.
Oh, what's a cyclic?
Can we just drop the
we-
perpendicular from C on BT? Sorry, BT, yeah.
Sure. Yep, that's a great solution as well. Let's call this X. Now, let's call this Y, let's call this Z. We have angle KYC is equal to angle KXC, 90. So KYXC is cyclic. That means angle YKX, which is the white angle, is equal to angle BCX. Similarly, we have CXZL is cyclic. So angle ZLX is equal to angle ZCX. This is the white angle. This is the blue angle. The sum of both of them is equal to the red angle. So we are done. Great. That's a good proof. So is the proof clear to everyone?
Can you also share your proof which you were telling?
Sure. It's basically equivalent, not much of a difference. Okay, what I was saying, if this angle is theta, then angle A prime AE is also is equal to 90 minus theta. Now you just need to find like the sum of this thing plus this thing.
How
Kind
is
of
that?
kind of results to the same thing. Like point is you can chase both of these angles.
Or we could just say that that's cyclic, right?
You
Since
can
BCD plus those perpendiculars to A.
okay, you're saying about this is cyclic.
Yeah.
Yes.
Can you tell how that's A dash AE is equals to 90 minus theta?
Question. 1 second. So like in general, if you have a triangle ABC with circumcenter O, the angle BOC is 2A. So this angle is 90 minus A.
Can
Because
you
OB
show
is
the
a-
diagram again? I could not see the center, I guess.
the center is B. Like look at here. We have BA is BE is BA prime.
Oh, okay, now I got it.
Yeah, no problem. Basically, the proofs are identical. There's not much difference in either of them. But so the key idea was to actually guess the point of tangency, which was A prime. And someone asked the motivation of A prime. So one motivation was to actually like make it into a triangle geo. Looking like this at the diagram is much better than looking at a horizontal diagram. So generally quadrilateral geos with some angle restriction or some restriction are most likely a triangle geo. Second, the way to relate C, like the C lies on a circle, and the circle is the reflection of circle ABD across BD. And the good point in that circle is the reflection of A across BD. So first of all, introducing A prime straight up gives you a cyclic condition. And it's like a great point because you're talking about C as locus, as in like how C moves, and A prime is a good point on that locus. So which means in some special case, C would be A prime as well. And say you want to test that special case, you can solve the problem for A prime, get the point of tangency as A prime, then prove it formally. So it's kind of like a leap of faith, as in the like the BT equal to TC problem, is that you just have to believe this is true and go ahead. And just because like the main motivation like I had was just because the way to characterize C are like the reflection of the circumcircle. And a good point on the reflection of the circumcircle is A prime. So let's just introduce it. So are there any questions about this proof or any problem before or any other general questions? I think I won't do any problem. It's almost time. Yep.
Source of this problem.
Source is, I think this is 2020 G3. It might be 2021, but I'm not pretty sure. But I think this is fine. Are there any other questions or anything else? I hope everything was fine and you enjoyed the class. I think we can stop here. Like, we'll stop recording.